All right. Well, instead of waiting for some arbitrary start times, why don't we just get you guys going? And the sooner we start, the sooner you can possibly be finished, right? So, good morning, everybody. I finally figured out how to pump the computer sounds directly into the Zoom meeting. So now they get shared not only straight to the video, the YouTube video, but now they can go directly to the Zoom meeting without having to use the specific share screen entirely, because the Zoom share screen is not always optimal. It doesn't get my combination of iPad screen plus me in the corner. So I think I've got things like ideal set where I want. It's just requires a lot of buttons to switch things up. Okay, that being said, we are in the process of graphing those wonderful, wonderful rational functions, super cool results. We're going to go over the answers, the results of the worksheet from yesterday, and then you're going to continue practicing and playing with them via a Desmos activity for today, okay? So that was it. The worksheet is done. Having finished that, I want to be really careful here. I'm pretty confident you are finished having to graph those by hand. Yes, okay? You'll still obviously need that skill and the content for the chapter test when we get there, but you won't be creating your own graph by hand on the chapter test, okay? So if that was the part that you struggled with the most, then relax. The worst of it is over. You are now free to let the computer do the hard creation work for you. That said, let's open up that worksheet and take a look, and let's see how you did. This was the one. Level 1 was just to do the front page, which had a few graphs, and then if you really wanted some extra practice, for level 2, you could do the additional graphs on the back side. So I'll go through all of those answers now. First up, finding the points of discontinuity. The points of discontinuity is everywhere the denominator would be equal to 0. So that includes the holes and the vertical asymptotes. Those are both versions of discontinuities. Okay? The holes are removable. The asymptotes are non-removable, because holes, they reduce out. You have like some factor on the top and factor on the bottom, and they cancel out. That gives you a hole. Asymptote did not cancel out. Okay? So just clarifying the language there, different sources will use slightly different terminology there. Discontinuity, holes, vertical asymptotes. So notice our discontinuities are -3 and 2. We don't have any holes, so we have vertical asymptotes at -3 and 2. Okay? And they're written as the equation of a vertical line. Same with horizontal asymptote. Don't just say it's at 0. Write it as y equals 0. Give me the equation of that horizontal line that is the asymptote. Okay. These ones are pretty straightforward. Holes are fairly uncommon in general. Most of these don't have any. This one has one. Here then in the second part, let me zoom in one by one, because that text is teeny tiny. You are again listing that critical information and then piecing it together to form the graph. And this is what I love about these graphs, is I am not persnickety. Like the fact that you have to go through like that point and then that, you're not graphing points when you're creating these sketches, okay? You are puzzling together, well, I know it has to fit this and has to fit that, and I have this intercept here, and the intercepts would be a graph point, but then you're trying to logic your way through, okay, reasonably, where must this go? It has to go here and here and here in order for this all to line up, right? You notice the function is negative. When it gets its way out here, it ends up on the negative side of 0. This one here, only one vertical asymptote. Explain 5's graph a little bit more? Sure. So again, finding those holes in asymptotes is the first step. Where does the function cannot equal, right? What values am I not allowed? And that would be 0 and positive 3 would cause the denominator to be equal to 0. I have no zeros, right? No value of x will cause the whole function to equal 0. So we have no crossing of the actual x-axis at any point. No holes to worry about, thank goodness. The horizontal asymptote is set to y equals 0 because the denominator wins the power war, right? This has an invisible x to the 0, which of course is just an invisible 1, right? 2 is greater than 0, so the greatest power on x is in the denominator. It wins. The function, when x gets really, really large, will tend towards 0. 1 divided by 1,000,000 is basically nothing. So that's where our horizontal graph. So you should always, always, always be able to start with the asymptotes, right? That's just extracting information from the equation. You have to be able to do that. And then it's like the one extra step, right? The very last thing is to interpret, okay, having those divisions, this general H pattern, notice that frequently the asymptotes are either a plus, or you could have 2 vertical asymptotes and we get some kind of an H. If you want 3 vertical asymptotes, right? It's always going to be some version thereof. And then your graph, right, fits inside those. This, flip around, flip like this, flip it that way, flip that way, flip that way, maybe something like that, right? So that it alternates each vertical asymptote, switches from positive, negative, until you have reason to believe otherwise. Unless, as I said, one of the factors is actually squared. It's like a double asymptote. So knowing it's got to be this kind of shape, our only option is, well, is it this thing or is it this way? Right? And that's where you look ahead. You can pick a point or look at end behavior. I tend to look at end behavior. I notice, hey, wait, there's a big negative in front. Oh, so overall, even when x is 1,000,000, yes, it's basically 0, but it's on the negative side of 0, right? It's negative 1,000,000th. So I know that this part of the graph, right, over on this side, this section past this asymptote has to be down here. And then I go, put that in, flip to the other side of the asymptote, continue, running in another asymptote, turn around, turn around again, back up, continue from the other side, right? It's like Pac-Man. You go off the edge one way and you come back from the other side. Okay? Any other questions on 5? All right, seeing none, here then is number 6, with just the one vertical asymptote. We are being treated to the guided tour here. Not a problem, we're just going over the answers. Okay. There is 6. No, 7. We're on 7. I lost count. So that one's probably a little tough just because the horizontal is at the half. But otherwise looks pretty much the same. There is 8. 8 has a slant asymptote. Why? Because the numerator wins the power war by exactly 1. Right? X cubed versus x squared. So when x is several millions, we got million cubed divided by a million squared, left with just a million. Remember, these guys are not the biggest power. They're basically worthless when x is a million. And so this cancels out, and that reduces out. And you got basically 1 million. Ah, but there's an invisible 1 here. It's 1/3, right? You could say f of x approaches a little y equals 1/3 x. And so we have, I bet if I drew this in here, if I connected my asymptote here, something like that, we could probably up 1 over 1, 2, 3. Yeah, look at that, right? Slope of 1/3. I wish they had actually put in a dotted line here, but it's okay. And this does not look like an F, does it? F, there we go. Why does the discontinuity have -1 and 3? Doesn't 3 cancel out when factoring it at the start? Yes, remember discontinuity includes holes and vertical asymptotes. All of those are types of discontinuities, right? One of them is removable. One of them is non-removable. But the full proper term for a hole is a removable discontinuity, right? Discontinuous, right? Where does the graph going along, doing its thing, suddenly have to stop? Oops, I didn't want it to do that, right? And I have to pick up my pen, move it over, and then go back down and continue. We have used the term discontinuity very literally. In fact, I would say almost the computer graphics applications have made it less clear of what that is. Right? When you could create a graph by drawing it with a pen or pencil, it was much clearer. It's like, oh, I have to pick up my pen, right? How many times do I have to pick up the pen and where? Right? Once at -3 and once at -1 and once at +3. Okay? Excellent. All right, then here is the back page. Oh, number 9 is a tricksy one on us, right? It breaks that the typical H format. Okay, look at this. We've got, once again, I can check this one because my horizontal asymptote is not on 0, so I can make use of the zeros, right? I know there has to be an intercept in here. So that tells me this has to go there. Okay, flip to the other side. Where is this going? I know there's another intercept down here. The only way for that to work is, well, I got to cross it. I have to do it, okay? You can never, ever cross vertical asymptotes. But you can cross horizontal asymptotes when absolutely necessary. Right? This is one of those instances. It is necessary in order to reach that 0, right? And then I've reached this vertical asymptote, Pac-Man in from the other side, flip it around. There we go. Right. That's how I would put that together. Mostly, right, it hugs and approaches horizontal asymptotes, doesn't quite reach it, but it is allowed to cross, right, in a very crisscrossy kind of manner. So just watch out for that. That is necessitated from this. This implies I need to do that. The only way it's going to work. One of those Sherlock Holmes, once you've eliminated the impossible, whatever remains, however improbable, must be the truth. Okay. Number 10, looks like we've got a slant asymptote here. It's kind of a little too big to fit within the bounds there, but it's there. Y equals negative 1/4 x is our slant asymptote. And once again, we are crossing this guy because I know I need these zeros. And this one too, right? And there is 11, another slant asymptote in here. Let me just give that a sketch in, there we go. You didn't have to find the equation for the slant asymptotes, let's say okay, but just know that one exists and recognize that it would at least be a negative slope there. That's good enough, okay? Negatively sloped because of the negative coefficient will get you a good enough sketch there. Okay, there's 12. 12 is pretty straightforward. Nice and simple, number 12. Okay. And 13, oh my gosh, we actually have a hole on 13. Look at that. I wish they'd used open circle instead of a closed circle. Gosh darn it. It's supposed to be an open dot, not a solid dot. Come on. Let's try to make it look like a hole. Oh well, what are you going to do? But otherwise, that one's not too bad. And there is 14, which is even simpler. Usually they put the hardest ones last. Not this time. Okay, final call for questions on this sheet. No? Okay, then I've got it pulled up here on the computer. I don't have it quite pulled up on the computer. There it is. Here then is our activity for the day. I want the student view, right? So link is on Google Classroom. We'll be running through this Desmos activity. And I'll be honest, if I had to do it over again, I would have had us do the Desmos activity before graphing by hand. I think that would have worked out a little bit nicer. So this will almost seem like a review and TUES after you got through the worksheet bit. So start with matching up process. How was it found? I've done one, possibly the hardest one here for you, right? So to find the holes, you have to set the canceled factors equal to 0, right? Because you'll cancel out the x minus 5 over x minus 5. So ZPP rules, technically you set x minus 5 equal to 0, solve for x to find out it's positive 5. Okay? We're so used to that ZPP part by now that we're like, what, set equal to 0? Oh yeah, I guess you do that part, right? And then it'll walk you through this process, right? Identifying the equations of the asymptotes, identify the slant asymptote, okay? Factoring the rationale into all of and identifying the pieces. Okay, we'll do that a couple times. And then finally, work from the graph to write the pieces. I like this one. This one we don't get from the worksheet, right? Work backwards. Here's the graph. Knowing what each of these parts are, enter the features, right? And we'll build up to creating the equation backwards, right? And slide 9 will draw directly from whatever you said here in slide 8. So I'll check, yes, x equals 5 is my vertical asymptote. So over here it'll say, your vertical asymptote, you said x equals 5. Right? So I know I need somewhere in here in my equation, start with y equals something, something, right? And then in my denominator, I need a thing that'll cause it to not allowed to equal 5, so I have a x minus 5 factor in there, and then you can, put your other factors up here, and whatever else you need, fill it in. I don't know about that 2x, I'm making that up. But this part I know needs to be there, because that's what's going to give me my vertical asymptote here. Okay? So that's what, I'll go through, right? From the graph, create the equation. And then, at what point does it flip over? Something, here we go. And then by 16, it'll give you, here's the features. Go ahead and sketch the graph digitally, and create it from the equation yourself, okay? Any questions on how the Desmos activity will work? All right, that's for the rest of the day. So you got a good 25, 26, 27 minutes to work there, and finish the rest of that for your homework tonight. Okay? And then tomorrow we dive into something almost completely different. Almost, but not quite completely different. Just leave it at that. You read about them over the weekend. Okay? It's not a spoiler.